Alright, so we've been trying a special case here. This is the 18th video. Uh, we've been thinking about this idea. So again, we're not sure if it will pan out. So let's at least say that it won't work. So suppose that, well, we have that order of g equals to p squared times m. We're going to consider a special case. P and m are relatively prime, okay? And let's suppose that there is some L subgroup of G such that order of L equals to P. Okay? Well, can we say that L cross, given that L is a group, can we say that L cross L is also a group? Okay, let's call L cross L S. Or we could just call it, well, we could just call it L cross L actually. We could call it S if we like. And so, well, what's the order of S? Isn't the order of S the same as the order of L times the order of L? What's the order of L? P. So what's the order of L times the order of L? Isn't that P squared? Right. So, I mean, maybe we can rush and say, well, haven't we just finished then? Well, firstly, how do we know there's a subgroup of order P? And also, how do we know that, well, L cross L is if L is a subgroup of G, are we saying that L cross L is also a subgroup of G, right? So, is this necessarily true, right? Because this is an ordered pair and this is just single elements. How can they be the same group? But perhaps maybe if L cross L, we're saying maybe if L cross L is not a subgroup directly of G, perhaps L cross L may be isomorphic to a subgroup K of G. Okay? So, but this still begs the question, well, what's the isomorphism? Right? Even if we had some L whose order is P, um, what isomorphism can we define from L cross L to K? Right? Or perhaps it's even better to think about it as from K to L cross L. We don't know which side is easy to conceptualize. Let's start with the L cross L to K side. Why? No, it's just flip of a coin, I guess. Intuition. Not sure. But let's see. So what do the elements of L cross L look like? And they just elements of G, so or elements of this group L. So let's say maybe, what do we say that? Maybe we should give them different names. So yeah, does it matter? Okay. So let H1 and H2 be elements of K. So aren't we saying that phi is some function? Again, we need to create an isomorphism that's taking elements. Okay. That's taking elements L1 takes elements L1 and L2, and the question is, well, what's that going to equal to? Phi of L1, L2, what's that going to give us in K? Can it give us something that actually guarantees us an isomorphism? So what about just the product of them? That is, what about if we send f of L1 to L2 and set it equal to L1 times L2? Is this going to be, well, is it even a homomorphism to begin with? What would we need to check? Wouldn't we need to check that phi of, let's say, L1, L2 times, let's say, L1 star, L2 star equals to, these stars, no stars. Forget the stars. Um, it's because L1 prime, L2 prime, let's say that. And don't we need to show that this is the same as, well, phi of L1, uh, L1 prime, uh, so what are we saying? Yeah, I'm just saying that this, if phi is indeed an isomorphism, doesn't it also need to be a homomorphism first? So aren't we saying that we want this to equal to, again, phi of L1 prime, L2 prime, right? So don't we want phi of L1 L2 times L1 prime L2 prime to equals to phi of L1 L2 times phi of L1 prime L2 prime, okay? So that's the question. Well, so let's see if it's indeed a homomorphism. This what we're describing here, the product of the things. So, well, let's see, what's just the left hand side gonna give us? Isn't that the same as phi of L1 prime, comma, uh, L2 prime? But doesn't that just give us L1 prime times L2 prime? Okay. What about the right hand side? What does the right hand side give us? Oh, right. Isn't that the same as just L1 L2 times, ooh, L1 prime L2 prime, right? So who said that L1 prime L2 prime is the same as L1 L2 times L1 prime L2 prime? So why must these necessarily be equal to each other? Are they equal to each other? That is the left hand side, which is L1 prime, um, L2 prime. Yeah, it's unclear why those have to be the same. So unless the group is abelian, well, you know, if the group were abelian, if G were abelian, right, then would it matter the order in which you multiply them? Wouldn't we eventually just, couldn't we rearrange them in any way? Okay, well, if G is abelian, or maybe L is an abelian subgroup. Okay, let's think about this. Okay, so if G is abelian, this appears to be a genuine homomorphism. Okay, but is it an is it surjective? Um, for any element of, for any k, for any little k element of k, can we, well, you know, we get to decide what k looks like. Um, okay, is the map surjective, or is it even injective? Let's see if in surjectivity would just mean that, well, we don't know what the subgroup k is. That's the problem. So, but, oh, okay, maybe we can just consider the image of L cross L, right? So, right. So if phi is a, if, okay. So let's make this clear. If G is abelian, if G is abelian, right? Okay, then, and we're saying that, and we're saying that maybe we're supposing that L has a subgroup of G. There's some subgroup L of G whose order is p squared. Okay, then we're saying that, look, the map phi from L cross L to L, from L cross L to some k. So, right, the map given by phi of L1, the one that sends L1 L2 to its product, just L1 times L2, well, that map right there seems to be a homomorphism. Okay. And if phi is a homomorphism, then it means that at least we know we know that the map from phi, the image of L cross L, right? So the map from L cross L to phi of L cross L under this property that it takes the elements and just multiplies them with each other. Well, this map is because phi is a homomorphism. Can't we say that phi of L cross L is also a group, right? So if phi is a homomorphism, isn't the image of a group a please do check that if phi is any homomorphism from some group, let's say G to H, then phi of G is also a group, right? So we're saying that phi from L cross L to phi of L cross L to the image of phi, well, we're saying that's a homomorphism. Oh wait, isn't that an isomorphism too? Right. Wait. Is this real? There appears to be something really wacky about this. Okay. We don't even need G to be a billion. Let's say instead that okay, G is our ordinary group, but L is a billion. L is the abelian one. So then L cross L given by L1 phi from L cross L to phi of L cross L given by L1 cross L2. Jeez. Yeah, this actually is turning out to be complete nonsense. Well, because think about it. What's the set of all L1 cross L2? If we're getting phi and phi is going from L1 to L2, well, what's the set of all L1 times L2? Isn't L a group? So L1 times L2, the set of all possible L1 times L2, isn't that just the group L? So aren't we saying that phi is going from L cross L to L? But how can this be an isomorphism? Right? What's the order of L? Isn't that P? What's the order of L cross L? Isn't that P squared? Right. So how can phi be an isomorphism? Right. At least how can phi be an isomorphism from L cross L to L? Right. So again, yeah, it's questionable whether this is helping us at all. That is, even if we got our best wish, even if we had that order of L was actually P squared, and even if we actually had L is a billion, would that ever help us in obtaining an isomorphism between L cross L and some subgroup of K? Right? Because again, the question still remains, can we find an isomorphism phi from L cross L to some subgroup K of G? Because if we can do this, we appear to be done. Well, it's bizarre though, because yeah, it's really bizarre because Isn't it true that if, let's say, theta is a homomorphism between G and H, right, doesn't that mean that theta is actually an isomorphism between G and phi of G and theta of G in this case, right? What that means is that all we need to do is what we're saying here. This seems to make sense, doesn't it? Because the image of a group is a group, right? That's the image of a group is a group if you're dealing with a homomorphism. So again, you could verify this, not necessarily obvious, but if phi is a homomorphism from one group to another, some group H, then phi of G is a group. Okay, but who said that phi, right? Whoever said that then phi from G to phi of G is going to be an isomorphism, right? Because sure, we know it's surjective, isn't it? Because, well, G is just phi of G. I mean, the image is phi of G, all right? We took out all the things that phi did not map to. But still, how do we know it's injective? How do we know that phi is injective, right? Maybe we have multiple things mapping the same thing. Okay, okay. So basically the thing here is that just because we are guaranteed a homomorphism, just because you have a homomorphism between G and H, doesn't mean that that same phi is an isomorphism between G and phi of G. It only tells us that at least the map is surjective if we go from G to phi of G, right? So, right, and that appears to be what happened to us here. Is we took a map phi from L cross L. We said if L is a billion, then if we define phi of L1 times L2 to be L1 times L2, well, that's going to give us, it's a homomorphism, okay, but it's going to be a homomorphism. If you look at just the image of phi, it's going to be a homomorphism from L cross L to the group itself, L. And so, and since the order of L is P, which is less than the order of L cross L, right? How could phi ever possibly be an isomorphism, right? Because the map is surjective, sure, but how do we know it's injective? Can it even possibly be injective? Right? So many questions there. And so this approach again, at least moving the obvious isomorphism, what we think of as the obvious potential isomorphism of going from L1 L2 to L1 star L2 doesn't seem to be helping us. So perhaps, right, perhaps we need to think of another isomorphism. What isomorphism can we construct between L cross L and some subgroup K of G, right? Other than the obvious L1 L2 equals to L1 L2, right, which again doesn't appear to be leading us anywhere. So let's try some other isomorphism. What other isomorphism could we think of here? Phi of L1 L2. What do we want to send that to in G? And it can't just be L, because again, if you just go to L, then and we want to guarantee that it's injective. That is, no two elements of L cross L are going to give us the same value in G. Yeah, what is, You know, one thing we do know is that L, if order of L equals to P, right, and we're saying that L is cyclic. So if order of L equals to P, alright, we just run out of time. So maybe we'll proceed from here next time. Just try to figure out if this approach is even worth our while and see if it could help us. If it doesn't help us, we'll have to abandon it and come up with think of something we haven't thought of before. Thank you very much for watching this video and have a relentless week. Bye.